Assalamualaikum and good day everyone. Okay, my name is Dr. Johanna. So, now I'm going to explain the part two. Okay, which is still under topic algorithm complexity analysis. Okay, in part one we have learned about the class complexity that we have, and then how are we going to calculate the number of steps based on the coding. Okay, and now is the time for us to learn about uh, other techniques that we can measure the efficiency. Okay, all right, so these are the order of increasing complexity. Okay, as what we have learned in part one, basically the complexity will start with O1, and then it will until O to the power of n, meaning that O to the power of n is the most complex. Okay, so you can see here that n is the size of our data. Then we can see that when the size is increased, okay, the value is also increased. Okay, so we can see that O to the power of n, okay, the value is increased so fast. All right, so actually there are two ways to determine the complexity time of algorithm. We have theoretically, which is by calculation manually, and we also have the practically, okay, whereby we can use any experiment or implementation. So implement the algorithms in any programming language and run the program. So this is practically, okay, and it will depend on the compiler, computer, data input, and the programming style. Okay, if let's say we want to determine the complexity time of algorithm, which is in theoretically, so the complexity time is related to the number of steps or operations. Okay, so the complexity time actually can be determined by first count the number of steps, then we find the class of complexity. What is the class complexity? We have learned before, right? O1, On, and so on. Or we can also find the complexity time for each step and then count the total. All right, so to determine the number of steps, we use the summation series. Okay, so if let's say here we have meaning that it start from the I is equal to 1, and then we are going to travel up to n values. Okay, so we're going to have here f1 until fn. Okay, because we start from 1 and it will end until n times. Okay, so the fi is actually statement executed in the loop. Now let's see this example. So in this example, we initialize the n is equal to 5 and the I will start with 0. So that's why here we have I is equal to 0, meaning that we are going to sum it, okay, up to 5. So meaning that we are going to have 1, 2, 3, 4, and 5. So we get 5. So the statement that represented by fi here, it will be repeated 5 times. Okay, so for the second example here, we can see before this, the I is equal to 1. But now the I is equal to 3. So that's why here we have I is equal to 3. But it's still, okay, will the summation still up to 5, the element number 5. So that's why here we can see that we have F3, F4, F5. Okay, so total that will be repeated is 3 times. Okay, for this one, meaning that it starts from the 1, I is equal to 1, but only one time. So we're going to have 1 lah. Okay, so meaning that it means that it will be executed only once. Alright, so these are the steps to determine the number of steps. Okay, so we have here, for example, 1 plus 1 plus n plus n plus n, then it should be 2 plus to the power 2 plus 3n. Okay, and in this case, we need to consider the largest factor. Okay, the largest factor in here. So that's why, since n is the largest factor, so that's why the algorithm complexity can be categorized as ON. All right, so these are the steps to determine the number of steps, okay? So we have here, for example, 1 plus 1 plus n plus n plus n, then it should be 2 plus to the power 2 plus 3n, okay? And in this case, we need to consider the largest factor, okay? The largest factor in here. So that's why, since n is the largest factor, so that's why the algorithm complexity can be categorized as ON. Complexity. Now, let's look at the next example here. Here we have 0, 0. Here we have n minus 1 plus 1. Okay, we got n. And then here we got n also. But we need to multiply with n. Since this for loop is under the for loop, then we have here n times n. And then for this case, we are going to multiply by 1, and it's again n times n. So the total of that will be n plus 2n squared. Okay, so you can see here that the largest factor here is 2n squared. Okay, so that's why the complexity time would be ON squared. All right. Series, okay, as shown below. Okay, so if let's say like this lah. Okay, so in this case we can see we have two. One is a, okay, variable a, and the second one is variable b. Okay, so you can see here that for the first loop here, uh it will be up to the n. Okay, and b is also up to the n. Okay, so here you can see a is equal to 1. Okay, and here you can see that up to the n, while for the b, again, b is equal to 1, but it will be up to n also. Okay, so actually the summation series is n, 1, 2, 3, 4 until n value lah. Okay, because this is until n value. Okay, so since we have here two for loop, so actually the formula would be n n plus 1 divided by 2. So we get n squared plus n divided by 2. So to prove it, if let's say we replace the value of n here with 4, okay, if we replace with 4, so that we can see that when a is equal to 1, a is less or equal to 4. Okay, so when we see here, meaning that if let's say b is equal to 1, okay, b is less or equal to a. So if let's say a 1, so here will be 1. Okay, because this is the first loop, this is the second loop. Okay, so we can see here that so this process will be repeated for 10 times, because when the a is equal to 1, we are going to execute only 1. Then we go back to the first loop. Then the a will become 2, all right? So when the a's become 2, move to the second loop, the b process will be executed for 2 times, okay? So this will be executed until it reach the a is equal to 4. So that's why we will get 10 times. So if we use this formula and we try to replace the value n with equal to 4, we able to get 10 times 2. Okay? Now let's try to look at this example. So in this example, we can see that if let's say like this is direct, then will be 1, initialization also 1, initialization also 1. Now, in this case, we can see that the i's start with 3. And we can see that the I is increased by multiply with 3. Alright, so that's why we will have log n base 3. Okay, then for the last one here, we have, okay, because here we can see that it is n, but since this one is under the for loop here, so that's why we need to multiply it with the log n base 3. Okay, and then for this one, okay, it will be multiplied by 1. Okay, because this is only out again, because it is under the previous for loop, so it need to multiply n and log n base 3. Okay, so same goes to this one and same goes to this one. All right, then when we calculate the total step here, we get 3 plus log n 3 plus 4n log n base 3. All right, if we remove the coefficient, we able to get that, okay, the total complexity is 4n log n base 3. Okay, but we need to remove the coefficient because the base is that we need to have log n base 2 only. Okay, because in asymptotic as classification, so the base of the log can be omitted, okay, by using this formula. Okay, so when we try to convert it, okay, so we can get log n base 3 is equal to log n base 2 is divided by log 3 base 2. So we are able to get log n base 2 divided by 1.58. So when we remove the coefficient, we're able to get O and log n base 2. Okay? Now, other algorithm, okay, to measure the complexity, we have amortized complexity. Okay, so the amortized complexity of algorithm for operation is such as insert, the search or delete is the actual complexity of the algorithm and operation. So the actual complexity of an operation is determined, okay, by the step count, okay, for the operation. So the actual complexity of a sequence of operation is determined by the step count for the sequence. Okay, so basically amortized complexity is when determining the complexity of a sequence of operations, actually we can at times obtain a tighter bounds. Okay, so the amortized complexity is actually like a tighter bound. Okay, so at least we have that measurement, okay, rather than have the worst case complexity. Okay, so these are the formula for the amortized complexity. Okay, it is like this. If let's say, okay, if let's say today, if let's say there is a cafe. Okay, sorry, I give you a very simple example. Let me erase this one first. Okay, if let's say, all right, there is a one shop whereby you able to get, okay, there's one shop whereby you able to get, there are 200 items which is you can buy 1 ringgit for each item. Okay, and then there is two items, okay, with the price of 200 that you can buy, okay, in that shop, A1 shop lah. Okay, so if let's say you have friends, two friends, okay, so if let's say you have friends named Aiman, okay, and then you have friends named Adilia. Okay, so for Aiman, for example, let's say you ask him, okay, Aiman, I want to buy everything in the shop. Okay, so how much you think that I should break? Then maybe Aiman, okay, because he wants to, maybe he was in a rush, okay, he just say to you, okay, then you need to have 200, okay, plus you need to have 200, okay, and then he asks you to bring 400. Okay, that is actually roughly. Then you have another friend named Adelia, for example. Okay, so maybe Adelia will calculate it. Okay, so 200 it times with 1 plus with 2 times 200. Okay, so based on this concept, okay, it shows that the Adelia formula is more accurate. Okay, so meaning that you are going to bring a money which is you can pay, okay, you can buy all the items that the shop have, okay. So that one is the amortized complexity. With the amortized complexity, it will help you, okay, to avoid the worst case, okay, to avoid the worst case. So if you're talking about the three methods of amortize, there are three methods, okay. We have the aggregate methods, okay. So in the aggregate method, we determine an upper bound for the sum of the actual costs and the amortized cost of each operation. It will start equal to this upper bound, which is divided by n, okay. And for the accounting method, we have this formula lah, okay. So mean that it will make sure that, okay, we assign the amortized cost so to the operations, okay, probably maybe by guessing, okay, then we are going to compute, okay, by following this equation, okay. And the last one, we have the potential method, okay. So for the potential method here, probably obtain using good guesswork, okay, that satisfies this formula, okay. So this is the amortized cost, this is the actual cost, okay, and then we have the probability cost here, okay, and we make sure that it will be greater or equal to 0, okay. Now let's look at example of the aggregate method, okay. So in this example, okay, normally for the aggregate method, we are using the dynamic table like this, okay. So look at this example here. We can see that at the beginning, we may initialize the table is empty and the size is equal to 0, okay. Now if let's say we insert one item at the beginning, the size is 0, right, and we want to add one item, okay. So it will insert one item, but it will be overflow because at the beginning the size is 0, okay. And then you insert 2. Oh, because you insert 2, the size is increased, okay. Now it become 2 and still overflow, okay. Now 2 actually will by the time you want to insert the third item, it will be 2 plus 2, so there is actually 4 slot here, okay. So if you want to insert the third item, no problem, okay. But if you want to insert the fourth item, now it will become overflow, okay, because the size now is 4, okay. So it will be 4 plus 4, so that's why here you will have 8 slots, okay. Now when by the time the slots become 8, okay, if you want to insert 5, 6 and 7, there's no problem, there's no overflow like the previous one, okay. So the aggregate method is similar like the implementations of the dynamic table arrays, okay. And the worst case, we may get O and square, okay. Now this is for the aggregate method. Okay, so basically from this one, okay, from this dynamic table, we get this table. So if we're talking about the aggregate method, we're going to have this table lah. Okay, so you can see that the first, definitely the item number that we want to insert, this is the table size, okay. And then we can see that, okay, 1 plus 1 is equal to 2, 2 plus 2 is equal to 4, 4 plus 4 is equal to 8. And you can see that, okay, it become 8, okay. By the time you add the 9 element, it will become 8 plus 8, which is 16, okay. So these are the costs. So we can see that the cost here, if let's say we remain, for example here, you can see here, right, in table size 4 and 4, the cost here from 3 will become 1 because at this stage, they will just reuse the size before, okay. And same goes to this one. That's why you can see here that, okay, 1 1 1, because we just reuse the slot that has been added before, all right. And then when you calculate, so we got O1, okay. All right, so for the NP completeness and AP hard, actually it considers some problem where giving us a guess for a solution, okay. Checking the solution to see whether the gas is actually okay or not, okay? And we've done it in polynomial time lah, okay? So even if the number of possible solution is exponential, so any given gas can be checked in polynomial time, okay? Which is, it is actually equivalently all possible solutions are checked simultaneously in polynomial time, okay? And thus the problem can be solved in polynomial time by our hypothetical magical computer. Now, look at this example, okay? So these are the example illustrations of the traveling salesman problem, okay? So if let's say we can see here that there are 5 vertices are shown, okay? There are 5 vertices shown here with ages and associated costs between, okay? So you can see these are the associated costs, okay? And these are the direction, the possibility directions, all right? So if the salesman visit the city in the order of A, B, C, D, E, A, he will travel a total distance 13. Okay, based on the number, this one we calculate. A better road would be A, B, D, C, E with a cost of 11. And the best road would be with cost of 9. Okay, so you can see that, okay, there are possibility. Okay, we have many directions, but which direction, which road actually will have a less cost. Okay, so this is example of the NP completeness and NP hard. Okay, so we can see the example lah. Okay, the travel salesman. Okay, so actually in order to improve, okay, the possibility that we have in previous slide, okay, so we propose to have these solutions. Okay, so the problem is that given a candidate cycle where we can quickly check the answer is indeed, okay, so meaning that we propose a solution like this lah. So a decision problem is simply one whose answer is either yes or no. Okay, so the suggestion is that input a complete directed graph K with positive distances assigned to each edge in the graph and in NTGK. Okay, so if the output is yes, okay, the total distance would be less than K, which is containing every vertex in G and no otherwise. Okay, no otherwise. So meaning that we divide it, okay, so that we have a decision problem, either it's yes or a no. Okay,